So, um, hi, my name is Howard and this is Collin. Today we're going to be presenting Leo. It's a programming language for formally verified zero-knowledge applications. And this is joint work that's been done with Raymond Chu, Alessandro Coglio, Eric McCarthy, and also Eric Smith. So as many of you know, we have a growing number of decentralized systems for running applications. Everything from financial systems to digital gaming, governance, social networking, and data sharing. Decentralized applications have become a foundation for new types of paradigms. And yet this new model comes with significant challenges. Namely, for one, we have an issue of scalability. This remarkable power of decentralized ledgers comes at a fundamental cost. The computational integrity of these systems is achieved via direct execution of state transitions. And in these systems, miners carry this overhead for transaction execution. And that itself presents two issues. The first of which is each miner has to re-execute every transaction along with its associated computation in order to verify its validity. And this technique is not only highly wasteful of computational resources, but it also creates a transaction throughput problem in that users who send transactions containing large or even unbounded computations run the risk of stalling the system. And in order to discourage denial of service attacks, current ledgers utilize mechanisms such as gas to try to economically bound such a risk. However, second, there's also this mechanism also fundamentally limits the expressivity as well as the functionality of decentralized applications. Just by having to re-execute each transaction, users are competing against one another for compute cycles for miners and effectively time sharing these limited resources across all parties. And consequentially, applications are provisioned these very tiny execution environments with limited running time, minimal stack sizes, and restricted instruction sets. And another fundamental challenge that we face is with respect to privacy. Current decentralized ledgers severely limit applications as a consequence of their design. Recall that the core strength of decentralized ledgers is also their core weakness, in that the history of all state transitions has to be executed by all parties. And in systems such as Bitcoin, this means every payment transaction reveals the sender, the receiver, and the amount. Not only does this reveal the private financial details of the individuals or businesses who use such a system, but it violates the principle of fungibility, which is a fundamental economic property of money. And this lack of privacy in and of itself severely limits the direct application of ledgers. When the state transition of every application is public, so is the history of function calls and its associated parties. And in practice, this limits the types of applications that current ledgers can support. And recent work has shown that a lack of privacy enables miner front-running and arbitrage attacks, and this creates a problem that we call miner extractable value. Beyond exploiting the inherent weaknesses of current ledgers for financial motivations, miners can prioritize transaction ordering at their discretion to create consensus instability. And these consensus layer security risks pose systemic risks to ledgers. So to address some of the shortcomings, zero-knowledge proofs have received a lot of attention recently for their ability to achieve strong privacy, integrity, and efficiency guarantees. And informally, zero-knowledge proofs enable one party, namely the prover, to attest to another party, the verifier, that a known computation was executed honestly for some private inputs. So for example, like in Bitcoin, Bitcoin requires users to broadcast their private payment details in the clear, and zero-knowledge proofs enable users to broadcast encrypted transaction details by proving the validity of the payment without publicly disclosing the contents of the payment. Now, this approach faces two fundamental challenges. The first of which is that decentralized applications today have weak guarantees of correctness and safety. Beyond correctly writing the application itself, there's also a lack of guarantee that the application is executed correctly and honestly. And unfortunately, this has resulted in serious attacks and critical bugs. But secondly, while zero-knowledge proofs are a promising technology for ledgers, writing efficient zero-knowledge applications requires specialized domain expertise. And not only does this cryptographic primitive need to be integrated into the ledger that it operates on or runs on, but applications in this construct must also be expressed in this mathematical representation that's simply unapproachable to most users. And so we present Leo, which is a new programming language for formally verified zero-knowledge applications. And fundamentally, with Leo, our goals have been to design a language that is, for one, composable, meaning users can combine arbitrary functions. In addition, Leo is designed to be decidable, meaning users know what the compiled program executes. And lastly, Leo is designed to be universal, meaning users should not need to run their own ceremony. Now, with Leo, applications achieve computational integrity, meaning executions can be succinctly verified by anyone. In addition, with Leo, applications are correct by construction, meaning compiled programs are formally verified. And so you may ask, how did we do it? And so let me break down how the compiler is architected. We decomposed this compiler for Leo into 3 primary stages. And in the first stage, we have here a compiler process whereby the compiler parses some Leo source code into an abstract syntax tree, or AST, and then it converts it to an abstract semantic graph, which is then used for processing. In the next stage, this ASG undergoes a series of compiler passes from type canonicalization to type inference, constant folding and copy propagation, along with loop unrolling and function inlining. And once all of these operations are done, then it goes into a final stage whereby the ASG is synthesized, it is optimized, and it's serialized into a Leo circuit. Now, for the sake of time today, we're going to focus on one critical stage of our compiler, namely that second stage, and elaborate in detail how we approach one pass of the compiler. You'll find detailed explanations for all of our compiler passes in the paper. Collin now is going to go over the objectives, the steps, and techniques that comprise this representative pass of the Leo compiler, namely for type inference. Collin?
Thanks, Howard. For those of you who haven't seen type inference before, it's an important phase of the compiler that assigns missing types to literals and variable definition statements. Let's take, for example, this piece of Leo code. When processed by the Leo compiler, the resulting output from our passive type inference ends up assigning legal typing to all of the variables in each method. With Leo, we use a Hindley-Milner style algorithm, which ensures completeness and soundness of our type inference compiler pass. We'd like to emphasize that this approach is crucial for the specific domain of zero-knowledge applications because the intermediate representation forces the original Leo code to be strongly typed. Otherwise, the compiler will fail to deterministically synthesize the corresponding Leo circuit. So we start by giving each untyped identifier in the code and each literal an unbound type variable. If we zoom in on the first let statement of function foo, we can see that we have not defined the type of identifier A. It's unknown to the compiler at this point, and so we assign type variable tau1, which is shown in green. Throughout this step, we add all known types and all unknown type variables into a symbol table, and we proceed. In the second step of type inference, we use the Leo language rules to form type equations between unknown type variables and the known types. Zooming back in on our green type variable tau1, our language rules for this statement in particular assert that the variable declaration for A must have the same type as its assigned value, 3. And so to the right, we can see the resulting type equation that forms. we assert that the type variable tau1 should be equivalent to type U8. The last step of type inference is solving. So we attempt to solve all of the type equations that we form. This is pretty similar to Gaussian elimination for linear systems. And we handle errors at this point. As all engineers understand, it's hard to write perfect algorithms. And so unfortunately, the cost of errors here is in the type inference algorithm for zero knowledge applications is greater than in other languages. For instance, like if we infer the incorrect type variable in a financial application, we may produce an incorrect output, and this could result in loss of funds. In decentralized protocols, you can risk selecting an incorrect R1CS gadget and potentially leave the protocol in like a broken state. And so we of course ask ourselves, like, how do we verify that our type inference phase is implemented correctly? So our approach applies formal methods to mathematically evaluate that our type inference phase is correct. We use a theorem prover named ACL2, which has the ability to generate proofs on formal specifications. To form the basis of these proofs, we constructed a formal definition of the Leo language that includes all of its syntax and semantics. Our end goal was to eventually build a verifying compiler, one that basically generates every time that it's run a proof of the semantic equivalence between its input and its output program. Let me walk you through how we use ACL2 to generate proofs of correctness for the type inference phase in particular. So we start just before and just after the type inference phase and obtain copies of the input program, which will denote AST, and the output program, which is denoted by AST prime. We then constructed a JSON to ACL2 converter, where we obtain equivalent data structures that can be read by the ACL2 theorem prover. These data structures are finally passed to the ACL2 theorem prover, along with a formal specification of the type inference phase. Both programs are checked against the formal specification, and we generate a proof that shows that the output AST prime is a type inference solution of the input AST. Mathematically, this is a binary relation, which holds exactly when AST prime is a correct output of the input AST for the type inference phase. It's good to note here that there may be more than one correct type inference solution for a given input AST. Other compiler phases will provide more flexibility here in implementing like the compiler phase. And so we do this for all of the subsequent phases, and by generating a proof for each phase, we end up composing proofs to obtain one end-to-end proof of the correctness of the whole compilation process. This end-to-end proof shows that the original Leo code is correctly compiled into a circuit and that circuit encompasses all previous Leo compiler phases and optimizations. We're hard at work right now adding more optimization phases to the compiler, and which will add to the modular design of it. And because of the way we've architected our proofs, they are modular as well. Howard will now walk you through our implementation of Leo and its performance.
All right, thanks, Collin. So we implemented Leo, and Leo itself is implemented in Rust, proudly implemented in Rust. It's open source, currently at 12 contributors and about 65,000 lines of code. And the programs that are written in Leo are formally verified using ACL2, the theorem prover that Collin has just mentioned. We are open sourcing this part soon, with partial passes already complete. And lastly, there is a Leo language formal specification, which is also to be public. It is open source with formal definitions that provide abstract and concrete syntax, and currently at over 70 pages. In terms of the performance of the Leo compiler, so we ended up benchmarking the compiler on 3 different sized applications, namely a 256-bit Peterson hash, a bubble sort algorithm, and a least squares linear regression. As you can see, the primary step that took the most amount of time is the time from ASG to R1CS, which namely has a significant number of compiler passes, as well as final synthesis. And as you can also see from this, as the size of the application grew, so did the time to compile. Now, in addition to just the Leo compiler itself, we've also built a lot of tooling and a lot of frameworks around it. And one of the main ones that we are actually going to be releasing this week is the Leo Playground. It's a new web environment that allows developers to write and test Leo code straight from the browser. This is something that will be likely released tomorrow as part of Developer Preview 2. It's our second major milestone in launching Aleo. And to jumpstart the development cycle, we've also built Aleo Studio. It's an IDE for writing zero-knowledge applications. In this particular case, Aleo Studio has Leo built into it from the get-go. And it's designed to simplify that development cycle to make it easy to publish a Leo package to the ecosystem. For Leo programs that are written, we've also put together a package manager. It's the first of its kind for zero-knowledge circuits. And it also has collaborative features like teams to allow it to be easy for people to collaborate, but also to make it easy for people to just import into a new Leo program that they're constructing. And in conclusion, the Leo website is leolang.org. We have the full paper online. Currently, it'll redirect to the ZK proof link. So paper.leo-lang.org is an easy way to redirect there. And lastly, the source code is open. It's online on GitHub, and you can find that at github.com/aleohq/Leo. And with that, we'll conclude, and thank you.
Thank you for your presentation. So we have 30 minutes until the top of the hour plus 20 minutes, whatever is your local time zone. And let's use this to figure out where Leo fits in our mindset about standardization, what kind of inclusion, documentation, merging, or challenges come up, and what would be the next step. Please speak up freely. I will moderate if we get too many collisions, but otherwise feel free to just unmute and speak.
Just a technical question about the language. Does it support non-determinism?
So currently, the language does not support non-determinism. So everything does need to be deterministic. And I guess there have been discussions in the past about introducing it. It would require at least some sort of a seed. It would require some sort of, some way to make it deterministic effectively so that you can reproduce. But otherwise, it would effectively need to be deterministic.
Just to clarify, I mean non-determinism in the zero-knowledge sense, where you have the witness is not completely constrained.
Oh, fair enough. Yeah. So in this case, yeah, it's deterministic.
Okay.
So to follow up on that, how do you see the integration of inherently non-deterministic components, things like verifying Merkle paths and guessing the result of a division and checking with multiplication, etc.?
Yeah, so there's a few ways to break it apart. Basically, the current path, as you saw from the compiler passes, takes you to a Leo circuit. And the assumption currently that we're making is that this will then be compiled into a proof system that will be run. However, it's also clear that one could do almost a trivial non-interactive proof of knowledge by merely sending over the witness if you're in a web context to other parties. And so you can dynamically synthesize the circuit and dynamically execute the program with respect to the context of that application. In that case, it would not go to a proof system. you would execute it in the clear, and that in and of itself like produces kind of a valid execution, or convinces the other party that you have that knowledge.
So maybe to follow up on that, because I want to clarify what the scope of Leo is to some extent. So is it just about specifying a circuit, and or I gathered from this that there's also some element of specifying an evaluation of a circuit, so what it means to get a get satisfying values for a circuit. Is that the limit of the scope of Leo, or does it also include pre-computation, which happens before you evaluate the circuit, or anything else?
So currently it's purely for specifying the circuit, and then for executing it. One of the aspects that we are looking to provide better tooling on is expanding the types of proof systems and curves that you can compile out to and execute on. But in terms of the steps leading up to it, we assume for the environment that you're running in, that you would collect all of the necessary inputs before passing it to the circuit.
Okay.
Have you written your own support for curves and proof systems, or are you using other libraries?
So currently we have one specific path, which is it's a graph-based path that's using BLS 12377. One of the things that we're looking to do and are also asking for input or advice on in terms of properly providing it is to support compilation targets. So for example, you could say something like Leo build -- native if you want it to run without a proof system, or you could say Leo build grot16 BLS 12_377 for that specific construct, or you could specify any arbitrary proof system curve, and that would provide for different types of targets to aim for.
Has there been any consideration given of, say, supporting ZK interface?
Yeah, so in terms of supporting ZK interface, it's definitely something that we've looked into. We're interested. More broadly speaking, one of the areas that we've been trying to optimize is the size of the final serialized representation. So there is actually from our co-authors, Alessandro and also Eric, who are on the call today, we've been looking at something called a PFCS, or something that we've been calling PFCS. It's a prime field constraint system. And the idea of that is actually to have a layer of abstraction above R1CS, one that is more general. So for example, in R1CS, you have two primary operators. You have addition and multiplication for arithmetic circuits. And in this context, you could introduce additional types of operators, maybe subtraction, division, inverse operations, but more so, you would no longer be bound by A times B equal to C as the constraint itself. You would have left-hand side equals right-hand side as an arbitrary type of constraint, which then could be reduced to an R1CS representation. And the advantage of having something like that as a format is that it would be more succinct or concise in its representation. You would need a deterministic algorithm to deterministically reproduce the corresponding R1CS, and so. But by doing that, it would highly compress the actual size of the program, which in our particular domain is interesting because the goal and the plan is to checkpoint and store these actual programs on chain via an on-chain circuit registry.
In this context, it's relevant to mention forthcoming extensions to ZK interface, or I should say proposed extensions that are coming from the SAVE program. So for context, within the SAVE program, because there are the multiple performers who produce programs for execution and multiple performers who consume them and plug them into cryptographic machinery, there was an internal need for interoperability between the two. And so the SAVE IR, intermediate representation, was created. It has actually two different syntaxes, one of which is based on ZK interface. However, it was greatly expanded in that context by adding additional representations. And right now there's a proposal under discussion for presenting custom gates, which are similar to what you just described, as well as loop structures and branches and other high-level constructs that various backends can exploit. Part of the discussions that we will probably be touching on in this workshop and explore more extensively after it, because this is all work in progress, is how to merge these extensions back into the succinct non-interactive world where ZK interface came from. And perhaps that would also answer the needs that you define now for a more general left-hand sides and right-hand sides.
Yeah,
if I can jump in briefly.
Go ahead, Alessandro.
Yeah. So just also another aspect which maybe also Aaron was alluding to with the ZK another aspect of PFCS is that you also have a hierarchical decomposition of constraints. So instead of having just one flat list, we can have, let's call it like procedural decomposition in some sense. You give names. So it sounds like from the way you're nodding that that's part of what also these extensions to ZK interface are meant to do. So it'll be very interesting for us to look at that. Yeah.
So Howard, one thing that is really clear out of this talk is that the Leo language and compiler.
You're very quiet. I can't quite hear.
Yeah, let me see if I can raise the volume quite a bit. This should be better.
Yeah.
Okay. Yeah, one thing that is really clear out of this talk is that the Leo compiler as an artifact is fantastic. One thing that is really not clear to me is the specification scope, right? You have taken implementation choices that are awesome, like Hidleminer, which gives you total type inference, principal types, etc., but that are not maybe necessary, right? If you had a nominal language, you could do local type inference. You've chosen to have a very fine compiler with ACL2. That's great. That may not be super required. And I'm thinking of somebody who's in the chat at the moment, which is Kevin de Wedderburn, who's written the Noir language, which has a backend towards Aztecs, Barenberg, Plonk compilation target. So could you help flesh out which elements among your awesome and gigantic technical stack you aim to put forward as specification target that will be useful to draw a commonly intercompatible big tent among languages aiming to help the writing of general-age proofs?
I think to provide a high level, and then Alessandro, if you want to add some of the supporting details on it, like the main objective with using this approach has been to enable formal verification. Like in order to have that support on the theorem proving side, we need to enforce strongly typed identifiers within the intermediate representation. And without doing that, it would be difficult to actually show equivalence consistently or deterministically. A lot of the heavy lifting or heavy work in terms of the formal specification has been to not only mathematically define and outline it in its abstract, but also concrete syntax, but also to provide a general blueprint for how each individual pass in isolation works, so that we can test the correctness of each pass in isolation in the compiler. I think to answer your kind of other question with regards to other types of approaches that I've seen or that people have seen, I think the biggest differentiating factor is with respect to that formal verification, that just having to use a theorem prover to enforce intermediate representations are being mapped and transformed correctly itself introduces a lot of challenges. Certainly we faced a lot of challenges in getting this one to, in getting this compiler to work properly with respect to that. And to also do it in a performant fashion. It's one thing to just have a representation that's very large and to prove semantic equivalence between that and another representation, and namely the ACL2 AST in this case. It's another thing to do that within seconds effectively to generate. And so a lot of the heavy lifting is to try to remove any assumptions that are in this IR before it's being passed to that theorem prover, and to provide a strong typing to all of the defined variables in this case, for this case of type inference, so that when we get to that stage, it's very clear that you can create a one-shot proof within seconds.
Yes, which is a great approach, don't get me wrong, but I'm not sure it makes for a standard, right? I mean, so the neural language has its own intermediate representation in CIR that Kevin Dre would be much better to talk about than me, right? But I am not sure that you couldn't put a theorem prover on the compilation steps. There doesn't seem to be anything fundamental apart from a considerable technical challenge that I don't want to remove anything from your achievements there, but like that it's not impossible to put a theorem prover on showing the equivalence of the transformation passes to me. And I may be wrong on that, but it would be great if we could capture the fundamentals of what is required of the IR and those transformation passes, so that we can take that formally verified approach. And so that we make sure that we have a standard that lifts all boats and allows people to show that they've achieved it without necessarily tying them into a specific IR, a specific approach. As you can say, Plonk, as you know, Plonk is a super interesting backend. It's great that we have a language that targets it. It would enrich Leo if both could achieve a kind of standard that allows both to be interoperable and to provide separate packets.
No, I understand your point. I guess like one thing to call out is that like as part of kind of those stages that we've outlined, the final representation in the circuit, whether it be R1CS or some other file format, or sorry, some other arithmetic format, doesn't happen until the very last stage of the compiler. So in this specific case, it's a PL problem that we're trying to address, in that we want to formally verify every one of the individual steps of this specific language, so that when we get to the point of actually synthesizing a representation, a mathematical representation of this program, you can choose different types of representations, whether it be R1CS or something like Plonk.
Yeah, essentially we give Leo a semantics that's sort of standard in terms of programming languages. You can think of Leo as a regular programming language that you just run, and it has a well-defined syntax, static semantics, and dynamic semantics, and that's all defined formally, and there's compiler passes to enforce all of these, including type inference that Collin described. And then at some point we turn that into R1CSs or possibly Plonks or other things, and then that's where the zero knowledge specificity comes in. Then you want to relate this traditional operational semantics of programming language to the R1CS semantics or Plonk or something like that. And we have worked out already the relationship of what that should be. So, but certainly I could use the approach for other. Yeah, go ahead, please.
I'm completely sure that this is the right approach, and that it is valuable to at least outline it and put it there as an example. But to be a standard, it would need to be abstracted away sufficiently so that you could go, oh, okay, we have this representation, the types bring us this, the formal semantics. What I'm saying is, if I look at the formal semantics of Leo, it's difficult to write something that respects that formal semantics without writing precisely Leo, right? That's my point. And I would love to see a standard that allows me to write something using a forward approach that maybe commits me in, if I want to respect the standard, into a transformation equivalent and programming semantics proof, without necessarily committing me into writing precisely Leo. There's even for Stark, so I believe that there's already a working group in the ZK proof workshop, not to just pine on Kevin Dre, who's got the Noir language with Plonk as a backend. There's already a working group for AIR for the intermediate representation for Starks, right? So ideally, we'd find a standard that defines the Leo approach, but for all of these instances.
So indeed, putting on our standardization hat, this proposal has many components, and we've already identified at least one place where it interacts with other efforts, like ZK interface. And I think we should drill more into exactly what ZK interface should provide in order for Leo to be able to express everything it wants to on the producing side. And I wonder other interfaces, as was just alluded to on the upper side of consuming the program, that would enable better interoperability with applications or with proving systems that reason about the high-level protocols. For example, the example from earlier, the Merkle tree verification reasons about the properties of Merkle trees, which are outside the scope, but someone would need to reason about them ideally formally. Is there anything that you would like to see to enable that kind of interoperability?
I think one of the main areas that we want to get right now, which could use some help, is with respect to the function signature. So when you call the program or invoke the program, one of the things that we do is to abstract away or abstract on a higher level what your inputs are, rather than just providing, say, the public and private inputs, which, as you know, because of intermediate allocations, when you synthesize a circuit, the private inputs can be very large. And so to provide some type of a structure that is more intuitive for a developer to call into or to assign, not only what items or what objects to provide, but also the types that are associated with them to enforce their correctness, would be very nice. And to provide a way to ensure that the representation, as we just talked about earlier, has a very succinct or compact representation that can be deterministically kind of unfolded or unrolled into an R1CS representation. That I think that would be, at least to the best of our knowledge today, a bit of a holy grail on being able to have a very good format, because it would not only provide for a program which could be very large to have a very small representation, but it would also provide for that program a very clear interface on what the expected inputs are, along with what the corresponding outputs would be. And I think that on a high level today, with just how everyone, including ourselves, have serialized our R1CS or our final outputs of circuits, looks like has been far less clear for, say, an average web developer. We have public and private inputs where the actual functions inputs and the functions outputs are inlined into that long assignment chain, and the constraints themselves are specifically this A times B equal to C format, which can be sometimes very verbose, and certainly for debugging purposes a bit challenging to kind of isolate under what scope or what function it was that this one constraint came from. And so to the extent that we can start to take those two aspects and create a layer of abstraction above, I think that would really help to boost the kind of usability aspects for such an interface.
So I think this is a natural starting point to discuss these interfaces and the interoperability with existing implementations or forthcoming ones around these interfaces on both sides. And ideally make Leo interoperable with other systems by having the similar frameworks and terminology and formats. And at that point, Leo can become an example of something that uses these interfaces with all of the many virtues you've enumerated, but allowing others who may have different tastes in programming languages and verification tools to substitute their alternatives using those same compatible interfaces. Thoughts on this attitude?
I first off am very strongly in favor of that. One of the things that we've just preemptively done to try to shift the conversation this direction has been to extract out what we had in early versions of Leo, a baked-in proof system and baked-in elliptic curve. We moved it out to another repo that's called Snark VM, and that's just for one specific compilation target, as we're calling it for now. But the idea being that the kind of point at which we checkpoint the final part of Leo is at that circuit part. And then like from there, you can basically from the representation in its IR form, take it out to different stacks, whether you want to go to Bellman or to libsnark or to ArcWorks. There's a lot of different common stacks that are coming up now, and while the ones I just named are just primarily R1CS based, there's also the Plonkwens, Bradenburg, and whatnot that are also coming up. And I think that to be able to go to those, it makes sense, at least on the Leo level here, just to get it to a program representation that is mathematical, and then reduce and derive for the specific domain that it plans to execute in, which in and of itself could also be native, meaning not non-proof system based. And this is something that we've been looking at, which may not be as of interest for zero knowledge proofs per se, but at least within the web context, that oftentimes between client and server who are running a specific operation, it is enough to, they're already handing this knowledge over that they could execute it in this environment. And if they want a proof for checkpointing or for auditability purposes with third parties, that this provides additional benefits and use cases. And so that's a native context execution. And we're trying to create this specific compiler to be agnostic to the underlying backend that it ends up hooking up with, so that it can be very flexible for those domains.
I was going to, excuse me, I was going to mention the Circ project, which is a compiler framework that it aims to support multiple front-end languages, and also it can compile to either circuits or an SMT solver representation. So the improved things about the program and SMT solver. Are you aware of that project, and how can you see any sort of possible interaction or integration?
I didn't catch the project name at the start.
It's Circ, C-I-R-C.
Yeah.
Ah, yeah, Circe. Yeah, absolutely. Yeah, we've definitely been very interested. As you can see, we have a lot of lines of code, and we'd like to make it smaller to the extent that we maximally can. The SMT solver approach from that paper actually looks to be far more elegant. I know that the implementation that was benchmarked was written in Haskell. And so there is a bit of a programming language barrier, at least for us. I know that there's I believe there is a Rust version that is currently coming up. And so to the extent that that becomes mature or is feature rich to the paper specs, we're definitely very interested. There's an aspect which we haven't touched upon currently, which is with regards to a core library in the language. A lot of the core library functionalities we've been thinking about using actually Circe for, because it would provide an easy way to basically get you to formal verification, but also to a much larger set of core library data structures and algorithms for use within the programs here.
Yeah, I'm very enthusiastic about the Circe approach.
Yeah.
So we have just a few minutes. I would like to focus on actionable conclusions. So let's take one more question, which may or may not be actionable, and then let's try to summarize.
Hello. Oh,
go ahead.
Oh, sorry, my mic was off all that time. Yeah, so I was trying to kind of figure out the difference between a SIR and the intermediate representation that you plan to create. It seems that your representation would be more flexible. The main purpose of a SIR was to basically be agnostic over the backends and be a bit simpler, I guess. It's basically arithmetic gates with unlimited fan-ins and black box functions. The black box functions, so I basically tell the backend, I want a Merkle proof. I don't care how you do it. Here are the inputs, here are the outputs. Do what you need to do in the middle. So that's where I think we kind of intersect.
Yeah, no, that's a great point. So
excuse me, who's speaking there? So I could, just for the notes.
It's Kev.
Kev, thanks.
Alessandro and Eric, you should probably correct me for anything that I say wrong here. This is starting to leave my domain. But one of the aspects that I think makes it nice, like in terms of what Leo's IR is and what it can be compatible with, is that we've really based ourselves onto an ASG here currently, an abstract semantic graph. And that's very much a PL problem that we're tackling here, is to enforce strong typing correctness and optimizations within the programming language domain. And then from there, it can spit out ASTs, which can obviously be converted or translated into arithmetic format. And that's certainly what we do with the latter stages for synthesis. But the optimizations and all the individual passes on the representation itself are purely from a kind of PL perspective, that it's not doing optimizations that we all kind of commonly know, like identity type constraints can be removed. Those types of optimizations aren't being performed within this ASG passes. These are very much very PL heavy optimizations.
Right. That makes sense. Yeah.
Yeah. So from there, like even for like the ACL2 theorem prover, like we take the ASG and then we spit out an AST of it so that it can then be used for formal verification. And so in this particular case, you could also take that, output it, and like basically produce like a arithmetic format from that AST.
That makes sense. Yeah. And you mentioned you chose the Hindley-Milner. Is it possible to choose something like Wand's algorithm? Because I imagine you might not want polymorphism.
Yes. Yeah, so there's several possibilities. We're using Hindley-Milner. Currently, the Leo type system is not polymorphic, but we still use sort of a Hindley-Milner style to infer the missing types. Essentially, wherever there's a type missing, we add a type variable, and then we set up type equations and we solve them. So in that sense, now it's not clear whether Leo will have a polymorphic type system. It might, but yeah, certainly there's, this is just what we're using now, but there's other possibility of other typing algorithms. While I'm at it, can I just briefly say something? I was wondering, you just, throwing it out there, something about, maybe standardized type systems for knowledge could be an interesting topic, so essentially having some, maybe there's already work, I'm getting the formal methods, I'm not so much in the zero knowledge, so I maybe say something very naive here, but something like, having a standardized type system to use in languages, and then standardized ways to compile those types and operations to circuits, that might be something that at least resonates with, standardization. I don't know.
Right.
So
Yeah,
let me
and
contextualize a bit and then try to wrap up the discussion, being cognizant that we have another proposal that to start discussing any minute now. So for those hoping to standardize the language-specific aspects, if I may be realistic or slightly cynical, this is going to be uphill in the sense that we have a large community and tastes differ drastically. So it will be difficult realistically to actually standardize certainly syntax, and I believe also the more nuanced parts of the semantics that are open to opinionated perspectives. With that in mind, I would like to focus for a couple of minutes on what we can actionably proceed on standardizing. And we already had the interface with the backends via ZK interface as a concrete candidate. So I propose that as an actionable consequence of this discussion. What else can we aim to make concrete progress on and set up specific meetings or working groups for?
I think it'd be really nice to have this PFCS be somehow standardized in case someone doesn't want to use the Leo kind of front end, but they can have all the capabilities of this PFCS.
So,
I mean, it is clear that there is several components that at least have been brought up that could be in a way generalized or could be modularized in order to be reused. I'm wondering whether there is enough people here, either that was part of the discussion or that would like to join discussion, and maybe we can continue this conversation in a few weeks' time after, say, potentially the authors have included some of these points of the conversation, or try to generalize some of the topics, at least briefly, in the paper.
Daniel, what's our current methodology for creating the channels for the working groups to work on? Is it still forum posts?
Yeah, so we have the forum posts, but we found that it works better to have a Telegram group, the old-fashioned Telegram. So
okay, so we'll append a Telegram group invite to the meeting notes. Everyone who is interested can join the group. We'll set up a meeting in a few weeks' time. We can prepare to that by coming up with more ideas for components to standardize as stepping stones. And let's proceed to our next presentation. Thank you all for the discussion.
Yeah, thank you all for sure. I will just say maybe to the authors, if you would like to take some leadership here, maybe you can create the Telegram group yourself and sort of post some updates on what's the status of the paper and what are maybe some of the topics. I mean, it would be helpful, to go hand in hand with the notes that Dara took. So.
Yeah, no, absolutely. And also the Leo formal specification doc, we will link in there. I realized that in this presentation, I did not link that. So I will add a link for that, which I think will be the most useful in terms of breaking down and showing you all the different components that we've mathematically formalized, so that we can then have a broader discussion from there. I also want to just quickly say, thank you to the ZK Proof Workshop, the reviewing committee, for reviewing this and also allowing us to present on this. And certainly thank you for everyone for your time.
Yeah, thank you guys.
And thank you, Dara, for taking notes.
Speaking of which, does anyone want to take over note taking for the next session?